In this video, let's take a look at IVT, EVT, and MVT. The first one up is the intermediate value theorem, IVT. When we see that word intermediate, we want to think of the word in between. What the theorem says, these are the ifs of the theorem, so the conditions. If the function is continuous, and if f of a is less than m, which is less than f of b, then f of x is guaranteed to equal m. So if you evaluate that function at some c, we will get m by the IVT. What do we use it for? When we are trying to guarantee a specific output value for a function, we are trying to determine whether a function ever attains a specific outcome value. What we say, well, since f of x is continuous, and you do need to say this, and f of a is less than m, which is less than f of b, then f of x is equal to m for some x value on the interval a to b by the IVT. And you can abbreviate with those letters. Here's our first example. If f of x is equal to x cubed minus 2, does f of x equal 0 somewhere on the interval? Well, first thing, have we met the conditions? Is it continuous? Yes, it's continuous because this is just a polynomial function. The next thing, is m between f of a and f of b? Well, here's what we're doing. We need to evaluate the function at those endpoints. So f of -1 will give us -3. F of 3 will give us 25. Does 0 land somewhere between -3 and 25? So yes, we've met both conditions. So we can justify, since f of x is continuous, f of -1 is less than 0, which is less than f of 3. F of c is equal to 0 for some c on the interval -1 to 3 by the IVT. These three spots that I've highlighted in the justification, these are the three things that will change based on your problem. Otherwise, the wording should be exactly the same. Here's a problem let's work through. Number 2, it says let f be continuous. So here's our first condition. We are continuous, and it's a closed interval, -3 to 6. If f of -3 is equal to 1 and f of 6 is equal to 3, then the intermediate value theorem guarantees which of the following? Okay, so between -1 and 3, we will have some value that equals 0. But does it happen at 0? We cannot guarantee that. So this one's no. Do we know anything about the slope at c? No, so we can't guarantee that one either. Okay, so let's see this one. -1 is less than f of x, which is less than 3 for all x between -3 and 6. We don't know of that for all x between -3 and 6. How about D? f of c is equal to 1 for at least one c, and that's true. This is our intermediate value theorem. And the last one, f of c is equal to 0 for at least one c between, these are not the endpoints, these are not the x values, so that one's also cannot be guaranteed. So just letter D. Here's another example. The functions f and g are differentiable, so we are meeting that first condition because if it's differentiable, we know that it's continuous. The table gives values of the function and their first derivatives at selected values of x. The function is h is given by h of x equals f of g of x minus 6. Explain why there must be a value f for r between 1 and 3 such that h of r is -5. Okay, so let's evaluate the function at the endpoints. H of 1, if we plug 1 into our function, we have f of g of 1 minus 6, and that gives us 3. H of 3 is f of g of 3 minus 6, and that gives us -7. So these are our y values. Does -5 fall between those y values? Yes. So since h of x is continuous, and h of 3, and we're doing from least to greatest, so that h of 3 comes first. -7 is less than -5, which is less than h of 1. H of r is equal to -5 for some value r on the interval from 1 to 3 by the IVT. Our next theorem is the extreme value theorem. When you see the word extreme, you want to think of extrema, max and minimums. So here are the conditions. You need to be continuous, and it needs to be a closed interval. Here are the conclusions. Then f of x is guaranteed to have both a max and minimum on that interval. What do we use it for? when we're trying to guarantee the function has a max or a minimum value. And what do we say? Since f of x is continuous and the interval is closed, f of x is guaranteed to have a max and a minimum on the interval a to b by the extreme value theorem. All right, take a look at this example. It says if f is continuous for x between or equal to a and b, so this is a closed interval and it's continuous, differentiable for x's between a and b, f of a is 3 and f of b is -7. Which of the following must be false? Okay, so let's see. F of c is equal to 0 for some c between a and b. Well, let's see. Does 0 fall between these two? Yeah, that's true. And that's true by the intermediate value theorem. F of x has a maximum on this closed interval. That's true by the extreme value theorem. That's this theorem that we're looking at right now. F of x does not have a minimum on the closed interval. That's false. Because as long as it's a closed interval, it's continuous and differentiable, then it will have a minimum value. And the last one, f of c is equal to -2 for some c between a and b. Again, that's true because -2 does fall between -7 and 3, and that is by the intermediate value theorem. The extreme value theorem is really only used to remind us to check the endpoints when we're looking for max and minimums. All right, here's our last theorem, the mean value theorem. Mean, and we want to think about average. What the theorem says, the conditions, if f of x is continuous and differentiable, then the instantaneous rate of change is equal to the average rate of change for some c value in the interval from a to b. What do we use it for? When we are trying to guarantee a function has a specific slope, and when we're trying to locate the place where a function's average rate of change is the same as its instantaneous rate of change. What we say, since f of x is continuous and differentiable, and f prime of c is equal to f of b minus f of a over b minus c. Oops, that should have been an a. There we go. For some value in c in a to b. All right, so here's our practice. Find the values of c that satisfy the mean value theorem. And I'm just going to work through one of these examples. So here's our function, and we have this quadratic and the interval from 3 to 6. So we need to find the instantaneous rate of change and the derivative of this quadratic. Well, if we use the power rule, that'll give us -2x plus 8. Evaluate that at c, and we have f prime of c is equal to -2c plus 8. Now let's find the average rate of change. So on this interval from 3 to 6, if we evaluate the function at 3, we get -9 plus 24 minus 17, which is -2. Evaluated at 6, we get -36 plus 48 minus 17, which is -5. If we find the average rate of change, -5 minus a -2 over 6 minus 3, that'll give us -1. So this is our average rate of change. We want to find where on the interval it's going to equal the instantaneous rate of change. So we take this -1 and we're going to solve for c. If I subtract 8 on both sides, I'll have -9 is equal to -2c, and so our c is equal to 9/2. We have another example. The function f is continuous for -2 to 2 inclusive, and f of -2 is equal to f of 2, which equals 0. Okay, so we're saying that the function evaluated at -2 and +2 are both equal to 0. So if I'm going to find the average rate of change, if you think about that, I'm going to have 0 minus 0. So the average rate of change is 0. It says if there is no c between -2 and 2 for which the derivative is equal to 0, there is no instantaneous rate of change equal to 0. So what's happening? Well, for some k between -2 and 2, f prime of k does not exist. So maybe we have a cusp or an asymptote, maybe a hole is going on, and so we just know that that does not exist. In our next example, let f be a function that is differentiable for all real numbers. The table gives the values of f and its derivative f prime for selected points x in the closed interval from negative 1.5 to 1.5 inclusive. The second derivative of f has the property that f double prime of x is greater than 0 for negative 1.5 to 1.5 including. Find a positive real number r having the property that there must exist a value c between 0 and 0.5. So we want to find a value c between these two. And f double prime of c is equal to r. Give a reason for your answer. So what it's asking is what number can be a guaranteed value for f double prime of c between 0 and 0.5. So to find this the second derivative, we're going to use the first derivative. Okay, so the instantaneous rate of change, or the second derivative at c, we're going to set that equal to the first derivative on this interval. So if we evaluate that function f prime at 0.5, let's see, f prime at 0.5, that's 3, minus f prime at 0, which is 0, so 3 minus 0, and then 0.5 minus 0, that's going to give us, well, 3 divided by a half is 6. So since f prime of x is continuous and differentiable, f double prime of c is equal to 6 for some value c between 0 and 0.5 by the mean value theorem.